Hello scientists, we're going to continue reviewing for the Unit 4 test. This is part 2 and this will be very brief, I promise. When we finished part 1 we were comparing the buoyancy and gravity vectors for a boat where you'd loaded a bunch of rocks in there. When you've loaded rocks you change the density of the boat. You're making the boat a different density, it has more mass per unit volume. So the buoyancy and the density, the buoyancy is going to change, it's going to be less, gravity is going to win in this case, and your boat is going to sink. Let's look at the next situation here. You take some of the rocks out of your boat and it's going to float a little bit better. And so the buoyancy is going to be more than gravity in this case, but it's not going to sink, it's not going to float really great, it's going to float kind of low in the water. So objects less dense than water, like this piece of wood, will float. Wood is less dense than water. If you have a very dense material like this steel ball, that's obviously going to sink. Stuff that's more dense than water is going to sink. And if it's the same density of water, it's going to hover in the middle of the water. When you have a fluid in an enclosed container and pressure is applied, the pressure within the system equalizes. That's Pascal's principle. What I have here is a very small hydraulic system, and when I apply more pressure in the system, the pressure is equalized, and you can see when I push this side down, this side goes up. This is an example of a hydraulic lift, or a small model of a hydraulic lift that might be used in an auto repair shop. So remember, pressure is equalized in a system, and that's what Pascal's principle is all about. So this demonstrates Pascal's principle. When you apply some pressure, when I push down on this side, the pressure is applied here, but it's also throughout the system, and that pushes this up. So if I push one side down, the other side goes up. If I push this side down, this side goes up. So let's match the density to the percent of an object underwater. The density of the object is going to be related to how much of the object is under the water. Water has a density of 1 gram per milliliter or 1 gram per cubic centimeter. So if you have a density that's 0.63, you're 63% of the density of water, and 63% of the object is going to be underwater. If you have a density of 0.84, that's a little bit more, and 84% of that object, more of this object, is going to be underwater than of here, because this one's denser. And if your density is 1.0, you're going to be 100% underwater. You're probably just going to hover right under the water because you have the same density of water as water. So you can see the matching here. If your density is 63% of that of water, you're going to be 63% underwater. If you're more dense, more of the object is going to be underwater. What's the difference between the speed of vibrating molecules in a solid, liquid, and a gas? Well, if you look within the curriculum, you can see this. Here you can see that the molecules in a solid are vibrating very slowly, so they don't take on the shape of their container. But the molecules in a liquid or the molecules in a gas can take on the shape of their container. Here's a liquid and a gas, and they're both taking on the shape of their container. So if you answered solids because they vibrate the slowest, that is correct. Solids vibrate the slowest and gases vibrate the most quickly. And solids don't take on the shape of their container because they vibrate too slowly. Let's see if you can match the properties of solids, liquids, and gases. I'll give you a moment and you can pause the video. Were you right? Solids vibrate slowly and they don't take on the shape of their container. Liquids vibrate at medium speed, take on the shape of their container, and still act like a fluid. Gases act like a fluid, take on the shape of their container, and their molecules vibrate the most quickly. The PTV rules apply primarily to gases. In fact, the PTV rule is called the ideal gas law. So let's talk about buoyancy and gravity. Pause the video and see if you can match. Did you do all right? Gravity is a fundamental force that's dependent on the mass of the planet you're on. Buoyancy is a force that depends on the density of the fluid. The density of pop is going to be different than the density of water because pop has sugar dissolved in it. And dish soap is going to have a different density than water as well. The force that it changes with the fluid changes. So there's a different buoyancy if you're floating around in soap than if you're floating around in water. What has to be true about forces for an object to float? Well, we know that density and buoyancy have to be different, or sorry, that gravity and buoyancy have to be different, and gravity has to be smaller. The gravity force has to be smaller. So there we are. Gravity has to be less than buoyancy if you want to float. What happens if you raise the temperature in a rigid container and it doesn't change the volume? Well, the pressure goes up. If you don't change the volume and you increase the temperature, what happens to the pressure? That one's a pretty easy if you have your PTV. You can put that on a pencil too. There's two pressures. There's the pressure inside a container, like inside a pop can, and the pressure outside of a container. Let's take a quick look at what happens when internal and external pressure are different. So if you heat a soda can,
careful that one, grab that one, turn it
and
over,
then you quickly cool it,
oh, nice.
the soda can is going to change its shape.
So it's literally it's the air pressure.
What's happened here is they heated the water in the soda can and they flipped it upside down in some cold water, and they quickly changed the pressure, or quickly changed the temperature. So when you quickly change the temperature, you change the pressure and the volume, and everything goes down. So the outside pressure, the pressure on the outside of the can, the atmospheric pressure, is greater than the internal pressure, and it crushes the can. It's kind of cool. So if you want to watch that can crush video over again, I'll put it in the notes for the YouTube. So what's a good estimate for the object's density if it's floating in the water? So remember we matched before the density and the percent underwater. So here there's about 50% underwater, so we're going to guess it's about 50% of the density of water. And yep, 50% was a good guess. Pascal's principle tells us something about what's going to happen to a tire when it's being pumped up. Remember, Pascal's principle tells us that pressure If pressure is applied to a system, it's equalized. So if I increase the pressure in one side, it's going to change and equalize the pressure in the whole system. The tire's not going to bulge. It's not going to do this when you start to pump it up. The pressure is equalized in the tire as you increase the pressure by adding more air molecules. So the pressure is going to be the same everywhere, and that's Pascal's principle. If you blow across the top of the piece of paper, what happens? Well, I have a piece of paper right here. Let's find out. If I blow across the top, does Bernoulli's principle say there will be lift and the paper will go up, or does Pascal's principle say the pressure will be equalized and the paper will go down? Well, it's not a hydraulic system, so Bernoulli's principle is going to be in effect here. As the speed of the air across the top of the paper increases, the pressure is going to decrease, and the faster I blow, the pressure decreases even more, and then the atmospheric pressure is more. So when the atmospheric pressure is more than the pressure on the top of the paper, because the air is speedier up there, the atmospheric pressure is going to push up. A hydraulic lift demonstrates Pascal's principle. So if we have Pascal's principle here, we're equalizing the pressure in a hydraulic system. There's a fluid here. So Pascal's principle, hydraulic system. Thanks for watching, everybody. And don't forget to try the raisins experiment at home. Put some raisins, some kind of dried up raisins, in some soda and see if you can get the density to change. Their density changes because of the addition of air bubbles, and then the air bubbles pop and their density changes again. So as their density changes, their buoyancy changes, and they sink and then they float.